Chemistry of water. Water has no taste, color, or smell, and we often look right through it. It covers over 70% of the earth, cycling from the oceans and rivers to the clouds and back again. It even makes up to 60% of our bodies. It is the main constituent of Earth's hydrosphere and the fluids of all known living organisms. Life as we know it would not exist without water. Imagining life without water is impossible. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with other multiple molecules simultaneously, it provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a surface tension, a high heat capacity, and a changes in density based on temperature. Water is often called the universal solvent, which means many substances dissolve in it. Water solvency has to do with the polarity and hydrogen bonding ability of water molecules. For example, when a salt such as sodium chloride is placed on water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive end of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or to associate with water. Why is this so important? Since our bodies mostly consist with water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond in their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds of water cause water molecules to stick together. It is a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this so important? Water fills the internal transport system of plants and animals. Because of these cohesive and adhesive properties, water allows the transport of the waste and nutrients within an organism. Water also has a high level of surface tension. Water molecules cling tightly to each other because water molecules at the surface are strongly attracted to each other than to the air above. The surface tension of water explains up why it builds up on waxy surfaces and why water-striding insects can walk on the surface of the water. Water has a high capacity for heat. It means that many hydrogen bonds that link the water molecules let the water absorb a large amount of heat without changing its chemical state. For example, liquid to gas or evaporation. It does not only stabilizes large bodies of water such as lakes and oceans, but it also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal temperature and are protected from rapid temperature changes. The density of water is based on its temperature. However, unlike many other compounds that contract when they freeze, the configuration of hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore, ice floats. If ice is denser than liquid water, it would sink, and the ponds in lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms to survive in winter. Now, let's talk about the pH level of water. What is pH? pH is a measurement of the concentration of hydrogen ions in a water-based solution. That 7 number is considered neutral or balanced between acidic and alkaline. If water is below 7 on the pH scale, it's acidic. If it's higher than 7, It means it is alkaline. A lower pH means that there are more hydrogen ions in the liquid, whereas a higher pH indicates fewer hydrogen ions in the liquid. In simple terms, pH is a scale from 1 to 14 that measures the acidity or alkalinity of a liquid. In the middle of the scale is the pure distilled water, with a neutral pH of 7. And as I have mentioned earlier, anything with a pH below 7 is an acid, and anything with a pH above of 7 is an alkali or base. pH plays an important role in the properties of a liquid containing water. These minerals makes the water very alkaline. Mineral buildup can cause various issues with water at home, such as making detergents and soaps less effective. The pH of a liquid will change depending on the ingredients inside. As a result, fluctuations are possible, even in two very similar products. Now, let's talk about the formation of water on Earth. With all this water around us, it is easy to take its presence for granted. But in the solar system, liquid water is almost impossible to find. So how did our planet end up so much with this substance? And where did it came from? As you probably know, a water molecule consists of two basic parts. Hydrogen, the simplest of all elements, has been around since the beginning of our universe. While oxygen, on the other hand, entered the scene several billion years later after the stars began to form. The massive pressure at the center of these fiery infernos was so great that hydrogen atoms fused to form helium. In a process known as nucleosynthesis, helium in turn fused to form heavier elements such as beryllium, carbon, and oxygen. When stars eventually collapsed and exploded into supernovas, these new elements were spread across the universe and combined into new compounds, like the now familiar H2O. These water molecules were present in the dusty clouds that formed our solar system, and more collided into our planet after its formation. But there is a big question that we don't have the answer to. How much water arrived on Earth? And at what time? If, as one theory goes, relatively small amounts of water were present on Earth when the rock formed, the high temperatures and lack of any surrounding atmosphere would have caused it to evaporate into space. Water would have been unable to remain on the planet until hundreds of millions of years later when our first atmosphere formed through a process called outgassing. This occurred when molten rock on the Earth's core released volcanic gases to the surface, creating a layer of cloud that trapped the escaping water. So how then did water get back to the planet? Scientists have long suspected that much of it was brought by ice-bearing comets, or more likely, asteroids that bombarded the Earth over millions of years. Recent searches have challenged this theory. In examining carbonaceous chondrite meteorites that formed shortly after the birth of our solar system, scientists have found that not only did they contain water, but their mineral composition matched the rocks on Earth and samples from the asteroid that formed at the same time as our planet. It suggests that the Earth may have accumulated a substantial amount of water early on that was able to stay put despite of the lack of an atmosphere. Though, asteroids may have brought more water over eons. If this turns out to be true, life may have formed much earlier than previously thought. So, We do not yet definitively know whether the water on Earth came from its initial formation, later impacts, or some combination of the two. Regardless, the water that runs from our showers, drinking fountains, and faucets is something that didn't just come from a nearby lake or a river, but first underwent a cosmic and chaotic journey to get here.